Hello, let's do Unit 4 review for APES. We're going to cover 4.1 through 4.9, and we're going to kind of make it in a concept map format. So the first thing we learned about in Unit 4 was plate tectonics. And so we know the Earth is broken up into these different plates throughout the planet, and plates are moving pieces of continental crust. And we know this crust moves in different directions. So one possibility is the crust moving toward each other in a convergent manner. And we know we get mountains and volcanoes and earthquakes. If it's pieces of ocean to ocean convergent boundaries, we also can get island arcs like Japan. And we also could get tsunamis, under ocean earthquakes. If the crust is moving away, we call that a divergent boundary. And we can get valleys. We can have the mid-ocean ridge at the ocean, which is where new crust is created. And that will also have really tall mountains and also lots of earthquakes and also volcanoes. And then we can also get a transform boundary where the pieces of plate are just transform boundary. Sliding past, we just get really big earthquakes like the San Andreas Fault. And we do not get mountains or valleys or any magma. No magma. And these are kind of the three boundaries, plate boundaries that happen. And we know these plates are driven by convection in the mantle. And convection, again, warm materials rise, cold materials sink down, and we get this flow, and that's like kind of a moving wheel, which is kind of like a conveyor belt. And the plates on top are just going to roll in the direction that the convection is happening. So that's what plates do. Now, I want to make sure I covered everything. Okay, so most plate boundaries are where earthquakes occur, or most earthquakes occur along plate boundaries as well as volcanoes. So these plate boundaries are kind of a big deal, those three kinds of boundaries: the convergent, the divergent, and the transform. And those are where most earthquakes and volcanoes occur. Okay, so an earthquake itself is going to form under lots of stress of the plates trying to move and overcoming that frictional force. And then that release of the stress is the energy, the seismic energy, which is the earthquake. Okay, and then hopefully you know we measure earthquakes on the Richter scale, and it's from 1 to 10. And that just measures the energy that the earthquake is creating, seismic waves. Okay, so these plates, remember there was oceanic crust and continental crust. I didn't give myself enough room over here. There's oceanic crust And there's this continental crust, two kinds of plates. Okay, so as this convection is happening and these plates are moving in certain directions and these boundaries are happening, the continental crust will start to break down and break apart, and we will get parent rock. And parent rock is where soil is formed from. So we need that parent rock to form soil. And we know soil forms from rock by mechanical weathering and chemical weathering. So mechanical weathering can be physical breaking of rock. It can be animals burrowing it down. Animals, can't spell. It can be water forcing it along and creating different impacts. It could be wind. And we can also have chemical weathering, which also could be water doing a reaction with the minerals in the soil or in the rock. So notice that this type of water is a physical tumbling of water, the movement of the water pushing the rock pieces around. And this one's a chemical reaction with the minerals in the rock. So water has kind of two purposes to weather things. And then wind also can, no, it's not. Why do I keep wanting to say wind is chemical? I've lost my brain. Chemical would just be the water. I don't know why I'm like obsessed with that. Sorry about that. My brain's jumping ahead. Okay. So once that starts to happen, we kind of see a type of succession underground, right? So parent rock leads to soil, and because of all this, we get these layers eventually over a whole bunch of time. But remember, there's some factors that we need to talk about that forms this soil, the stuff that makes soil happen. So the climate is a big deal. How much water or moisture is there? What's the topography like? Topography. What's the parent material like? And so all of these factors are going to help form the soil and the vegetation, what kind of plants grow there. And so that will form our soil, and we'll get this soil profile. So if we dug down into the ground and we took a little cross cut of what was going on, we'd have organic matter on the top, so dead leaves, litters, the dead decaying animals. Then we'd have a nice dark layer of soil, which would be the topsoil. This is layer O for the organic stuff. And then we'd kind of have that lighter color, which is the leachate, right? All the minerals that are going to leach down. To the kind of light brown soil. Which is going to be our B layer. And then we have our parent rock material, which are kind of chunks of rock down here. That's going to be your C layer, parent rock. And then this is the R, which is the actual continental crust, the tectonic plate. And those are kind of our layers of soil. But remember, one of the big factors is lots of time. It takes tons of time for this to form fully. So this is not an instantaneous process. And sometimes you can even look at a soil profile and see where it is in its development stage. Where is it on forming a nice mature soil? And you will see a relationship to succession. on top. So judging by what plants and vegetation are or are not present on top, you can see what the soil is going to be like below, or predict what the soil is going to be like below. Okay. So we judge our soil on a few things. So this is how soil is formed, but the soil composition, what the soil is made of, is a big deal, and it actually has a part to play in what is able to grow in our soil, what can or cannot grow. So remember, there's a tiny particle, which we call, we don't call it sand, we call it clay. Tiny particle called clay. We have the medium-sized particle, which is silt, and we have the larger particle, which is sand, plus particle size. Let me label it. So this is particle size. And then we have another factor of water holding capacity. How well do these particles hold water? So we know that clay holds it better than silt, which holds it better than sand. And then we have another factor we measure with, which is porosity. How quickly the rate of water flow through the soil. And that one, we know that sand is greater than silt, which is greater than clay. So notice that these two are opposite each other. Make sure you get that. Okay, so the particle sizes really can determine how good the quality of soil we have. So when we get to soil quality, we kind of evaluate it in that soil triangle. And we have the sand, and we have the silt, and we have the clay. And ideally, we want to be in the loam, a little bit of each type particle. Each particle has a purpose. Clay holds water, sand lets water go through, silt holds all of the stuff in place, and it's kind of the best of both worlds, and it holds the nutrients, the nitrogens, the phosphorus that the plants need. So a loam is really, really ideal. Clay has good purposes, like clay is good in landfills. They have a good water holding capacity. So when you have all your stuff in a dump and it rains, you don't want all the dump pollution to go into the groundwater. And if it's a clay lined landfill, it's going to hold and pool that water so it can be pumped out and not get into our groundwater, our drinking water tables. So clay has a good purpose for that. You wouldn't want to put your landfill with sand because that water would go straight through, drain in, and all the pollutants from your garbage would get into your groundwater. Probably wouldn't be so healthy. Okay, so by knowing the quality of our soil, that helps us to know how to treat soil. What nutrients does it need? And that's why we did that soil test. And we had that kind of soil lab. And we tested for nitrogen and phosphorus and potassium and the pH of it. And it tells us how to amend the soil to let it grow stuff, to make it more fertile. I'll make that green for fertility, more fertile, so we can grow the vegetation that we want. So that was kind of our soil situation. And then another super important thing, which I can't really find a super great way to transition to from here, but we'll just do it, is the atmosphere. So we also learned about the atmosphere. And the big thing with the atmosphere was the atmosphere graph. So if this is temperature and this is elevation or altitude, and we realized that in the atmosphere, things are divided by density and temperature. And we have these layers of the atmosphere. And there's a really famous graph that shows us that as the higher we get, we start to go a little cooler. But then there's a point where it starts to go a little warmer. And there's a point where it goes a lot cooler. And then there's a part where it goes a lot warmer. And then we kind of get out. And these layers are as follows. So the very bottom layer, the one that we live on, is called the troposphere. So that's the layer with oxygen, with water, the weather, the life, the people, the animals, the plants. Most of anything that's going on happens in the troposphere. It's probably the one that has the most pressure because it's, on the bottom. The layer after that, if you look, it starts to get a little bit warmer than the troposphere, and that one is called the stratosphere. And the stratosphere has the ozone layer, O3. And ozone layer's job, again, is to block out UV light, which is a cancer causer. Cancer. It can also cause cataracts, the yellowy part in your eyeballs, cataracts. And in plants, it actually can affect plant growth. It actually interferes with their ability to do photosynthesis if there's too much ozone. So plants get affected by this as well. The next layer is the middle one, the mesosphere, the middle layer. And we talked about that. It gets pretty cold. And so if a hot meteor comes out, it helps to break up those meteors when they enter our atmosphere. And then we have the really warm layer. Let me get a different color here. Okay. Then we get the thermosphere, which is our hot layer. It gets really warm. And that's where we see the auroras, the aurora borealis, because it interferes with the sun, cosmic radiation, and the Earth's magnetic field. And then our last one, I'll do it in this really cool galaxy thing, is the exosphere, where we exit into space. Okay, so that's kind of the atmosphere situation. And here, temperature increasing and decreasing, and then increasing and decreasing elevation. So that's the general basic shape of the atmosphere. And then we want to kind of focus on the troposphere itself. So the troposphere is about 70% nitrogen, unusable nitrogen from our nitrogen cycle days, right? That nitrogen has to get fixed into NO2 for the plants to be able to use it. And then about 20-ish% is oxygen. And then the other remaining 10% is a bunch of other gases, other small amounts of gases in our atmosphere. Okay, so this is the atmosphere kind of pie chart. Okay, and so then what's going on with our planet? Well, we've got this global wind, right? So wind helps to circulate the air, and so does this Coriolis effect. And the wind helps kind of mix the temperatures. And we also have kind of some convection, that the wind is driven by. And so we know we have these different cells that go in different directions and in different layers. And so we have like the Hadley cell, got the Farrell cell, and we've got the polar cells, which you watched videos on. So the reason that the wind is important is because of the way the Earth is heated. So remember, the sun hits the Earth differently, right? So we have this thing called solar insolation, which kind of determines the intensity that the sun hits. So at the equator, it's very warm because it's a small surface area. And up here at the poles, it's cooler because it's a more spread out energy over the surface area because of our spherical shape of our planet. The oceans do the same thing. And so we have ocean currents too that move in those kind of circular motions, which were gyres, surface currents. And then we have the deep, deep ocean currents, which is kind of one big conveyor belt. And it takes about 150 years to make a lap around that big, huge ocean current conveyor belt. And those are driven by density. So remember, when it's really cold, the fresh water freezes at the poles, left with a bunch of salts in the water that get really heavy and they sink down. And that's when this density starts happening. They get by the equator, they'll warm up and spread out, and they'll become less dense and start floating back up to the surface. So wind and water play a really important part on how our Earth's heat gets distributed. So one of the big ideas is the Earth's heat is unevenly distributed. And because of that, we rely on wind and water, ocean currents, to fix that and spread out the heat. Okay. I probably should mention, let's do it over here. So we've got ways to distribute the heat: wind, water, and then seasons. Because the Earth is tilted, seasons happen, and that also helps tilt of Earth to distribute this heat. All right, let me check, make sure I wanted to say any more. Okay, so all of these things also affect the Earth's geography and the climate. So if we go back up, plate tectonics affect our geography. Obviously, it's forming mountains and valleys and oceans, and our climate, because again, the way air masses work and how they form is they kind of take on the properties of what they're over. So plate tectonics are definitely going to affect that. The atmosphere is going to affect that. The wind's going to affect that. The ocean's going to affect that. So it all comes down to climate. So let's talk about that for a second. So climate is influenced by plate tectonics. Climate is influenced by wind and water current. Climate is affected by geography, which is really a subset of plate tectonics, right? So we know in geography, altitude in the troposphere, the higher the altitude, the lower the temperature. That's definitely going to affect our climate. We talked about that rain shadow effect. So when clouds are lifting up over a mountain, they're going to drop their water content, all their moisture. And by the time they get to the back side of the mountain, they're going to spread out and come down and be more dense, and they're going to warm the backside of the mountain, and we're going to see more desert-like climate. Whereas on the front side, because it's dropped all the rain, we're going to have all this vegetation and a more temperate climate. And that is again called the rain shadow effect. Okay, and then the final kind of climate mystery card is that El Nino La Nina season. So we've got this ocean, and remember in the ocean, we've got this deep current coming upward toward the Americas. So here's North and South America. And we have this current sweeping up all the nutrients. And remember, that is called upwelling, which is how fish get nutrients. And here's those fish. So if there's no upwelling, or if upwelling is slowed or altered in any way, fish are gonna die. And then we've also got kind of Australia and Asia's over here in the Pacific Ocean scenario. And we've got these wind currents. And so normally the wind is blowing warm surface currents this way, and we're getting the air currents moving that way, and that's making this upwelling happen. So this is normal. But when El Nino time comes, or the El Nino Southern Oscillation, and so things reverse. So this wind can like slow down, it can reverse direction, and so can the currents. And so the upwelling either isn't as extreme or it actually stops altogether, but these nutrients don't make it up high enough for the fish to get anything. So fisheries suffer, fish are actually dying, and then we see all kinds of weird climate situations worldwide, which are on your slide that you saw before. So we see things like drought in areas that don't have drought, and we see flooding in areas that usually have drought. We see hurricanes where the locations are, they shift. We can see disease growing and spreading because of the way things have happened. We can see a lot of economic damage from the winds and the flooding and the landslides. We get landslides in California, land or mudslides. So there could be a lot of effects of this big sudden change in our weather. And this is in a cycle that is somewhere between 6 and 11 years, but sometimes we get a surprise and it comes every 2 to 3 years. So it's kind of crazy. So now that we have satellite technology, it helps us to track it a little bit better, and then know that when El Nino corrects itself, we get La Nina because the girls have to fix everything. And the La Nina event, which we are actually in this year, is correcting back to normal conditions. Okay, so that's kind of Unit 4 on a crazy Miceli mind. I like to make these concept maps because it lets me kind of see everything in one shot. So feel free to draw your own and make your own connections. And I even think it might be valuable to make one for all 4 units and try to hook all of it together. I might make one and share it with you, but sometimes what works in one person's brain doesn't work for another person's brain. So your concept map of this unit could look totally different than mine, but as long as it helps you connect the content and understand it, it's totally worth it. So hopefully this helps, and we'll talk again soon. Good luck on your final.